Well, today we're going to be doing the 2018 higher level paper 1, question 8. It's a question that has some functions and calculus in it. A bit of a tricky one if you don't know your terminology for calculus. There's some kind of differentiation that you wouldn't be used to in everyday differentiation. So we'll start off with part by reading the question and with part A. So the graph of the symmetrical function fx, and it's there, is shown below, and it gives this diagram, which I've attempted to draw. And in part A, it asks us to find the coordinates of A, the point where the graph intersects with the y-axis. Give your answer in terms of pi. So what we know, when something intersects the y-axis, it means it intersects it at the point 0. It intersects it at the point 0 something, because the y-axis is on the x. The y-axis intersects the x-axis at the point 0. So A is 0 something, so we'll call it W for now. And we have our function and we have our input x, because this function's with respect to x, and we have our output that we're trying to find. And if we have our input and we have the way of getting to we have our function, we can find our output very easily. So we do f0 goes to 1 over the square root of 2 pi e to the negative 0 squared. So this, the e to the minus a half, 0 squared, that goes to 1, because something to a power of 0 goes to 1, as we know. And 1 multiplied by 1 over square root of 2 pi is equal to 1 over the square root of 2 pi. And that is our answer, and we can leave it like that because it says that we can leave it with respect to x. You might want to write the final form in like this, just like as a coordinate. Maybe some examiner might be a bit sticky about it, but it's just like that. So the paper asks us in part B of the question, it tells us that the coordinates of B are minus 1, 1 over the square root of 2 pi e. So it then asks us to find the area of the shaded rectangle in the diagram above, and it has it just here, and it tells us it's just this rectangle here, and it tells us that it wants that area corrected to 3 decimal places. So the key part of this part of the question is remembering that the function is symmetrical. So we know that here to here is 1, so here to here is also 1. And we also know that this part's 1 over the square root of 2 pi e. Because we know that that's the y value, which is the height up. So we'll draw the new rectangle up, which is 2, 1 over the square root of 2 pi e, and then 2 multiplied by 1 over the square root of 2 pi e, you get 2 over square root of 2 pi e. And the question asks us to put it to 3 decimal places, and it comes out to 3 decimal places as 0.484. Just throw that into your calculator, you don't need to do any more calculations for that. And we'll just move on to part C now. Right, so for part C, it tells us to use calculus to show that fx is decreasing at C. So what it means by that is to use differentiation to show that the slope the instantaneous slope at the point C is decreasing. So we're going to just use a little bit of derivation to figure that out. Because the function f(x) will give us our y function, but f dash x, which is the differentiation version of it, will give us the slope when we put x in. So we'll take out our constants because they won't change under differentiation. And that is e to the negative half x squared. So when dealing with exponential to the power of an x function, we deal with it this way. We do d of e ux it comes out as that, and we just multiply it by the differentiated version of ux. And in our case, our ux would be minus a half x squared. So this goes to 1 over the square root of 2 pi. I have to write 2 pi e there. 1 over the square root of 2 pi, and it goes, it's e to the negative a half x squared, and it's multiplied by minus x. Okay, so we differentiate that, and we bring 2 down, put the 2 in front, and we minus 1 from the power, and that takes away the half, so we're just left with negative x. So we can't really simplify that down much more. And also, when you're dealing with questions like these, they'll often not get you just to do the first derivation, they might get you to do the second derivation, which is quite common. So I would leave the function in the form with the constants kind of grouped together, so you can deal with your x's on their own. I might put the minus here. On their own, so you can put your x's on their own, so you can just deal with them and not have to worry about miswriting a 2 pi or something. Anyway, this isn't done yet. We have to find the slope at the point C. So we know that the coordinates are C, and because it's symmetrical, it's minus 1 at B, and the same height over at C, so it's minus 1 whatever. Minus 1 over the square root of 2 pi. Right, so we throw that into our calculator, and the answer we get out is negative. You really don't need to know what the actual slope is. It just asks us if the slope is decreasing, so you could just write this minus sign circled, and then you could just to make sure, you can say therefore slope decreasing at C. And you can just leave it like that, and that's all you have to do for part C. B of the question, it asks us to show that the graph of f(x) has a point of inflection at B. Point of inflection, that is a word, it's a term used in calculus quite a lot in dealing with functions. It means it's the point in where the slope of the graph turns starts to change from increasing or to decreasing, or vice versa. Well, that's quite wordy. What it kind of means is, so the slope is kind of increasing, increasing, and increasing. And then at some point, it turns. It stops increasing and starts to decrease, because the slope is 0 here, and it's close enough to 0 somewhere around here. So it has to go all increase, and then at some point along here, it starts to stop increasing and start decreasing. So now that we understand what the point of inflection is, often called the turning point also, what does it mean mathematically? It means the second derivative is equal to 0, so f dash dash of x would be equal to 0 at the point of inflection. So we are to prove that the point has a point of inflection at B. Coordinates at B mean that right, 0. And we're to prove this. Okay? So our first priority is getting the second derivative of this. So f dot dash of x would be, we have our constants out in front. And then we have x, e. Okay, and because there's two numbers here, that means we are going to use, and they're multiplied by each other, it means we're going to use the chain rule. And the chain rule is we're going to add in this minus 1 over the square root of 2 pi after, but we're just going to deal with this independently first. We'll get x multiplied by the differentiation of e to the negative half x squared. And we add that to the differentiation of okay, so we already know what this is differentiation because we did it up here and in the last part of the question. So I'm not going to explain what we do here because we already did. So we get x multiplied by minus x e to the negative a half x squared plus 1 multiplied by e to the half x squared. Let's see. Yeah. So we multiply that out and add the we multiply out, and we get e to the negative half. We have to make sure that we add back in our minus 1 over 2 pi. And minus x squared again. So we have it like that. Now what we do is, that's our f dash dash of x, the second derivative of our f function. So what we're going to do is you input your minus 1. So input minus 1, and I don't have space on the board, but you input that in, and you'll get 0, and that proves that the turning point is at B. And I would just, after you have that written out on your You put that into the calculator. I just write, therefore, point of inflection at B. And that lets the examiner know that you understand what this means and make sure that they can't not give you any marks. The examiner is not trying to give you, yeah, we'll just cut out that last sentence.